Let's say you were deciding whether to go out. There are two things you care about. Will a friend come with you? And is the weather good? Each of these feels like a yes or no toggle, and depending on how much you care about each one, you might lean toward going or not. This strangely is the idea behind the perceptron, the first mathematical model of a neuron, and in a way, the beginning of artificial intelligence. But a few years later, a paradox would destroy that future, and almost no one saw it coming. But first, let's see how a perceptron works. Here is the basic setup. You take inputs, just simple 0 and 1. Each input gets multiplied by a weight. Essentially, a way to say how much does this factor matter? Then you add all those weighted inputs together, along with a bias, a kind of built-in preference. And finally, you pass the result through a step function. If it's above some threshold, the perceptron outputs a 1. If not, it says 0. Imagine a graph where one side says output 1, the other output 0. A single line slices through them. That's the perceptron's decision boundary. It's simple, but something about the simplicity is elegant. This idea goes back to 1958. Frank Rosenblatt built the first perceptron model, inspired by how biological neurons fire. Back then, the media called it a breakthrough. Some lines suggested it might one day walk or think. It could classify simple images and even learn from feedback, all using just one line of math: multiply, add, compare. And for a while, this felt like the future. But then came a problem, a paradox with two inputs called XOR. It returns true when either input is 1, but not but. Seems trivial, but no matter how you adjust the weights or bias, a single perceptron simply can't model it. Try yourself. Plot the points for XOR on a graph. No matter where you draw the line, it fails. There is no straight line you can draw between the output 1 and output 0. And that's all a perceptron really is. A tool to draw lines through data. This limitation hit her. In 1969, a book by Mervyn Minsky and Seymour Papert, pioneers of early AI at MIT, laid bare the perceptron's flaw. Funding dried up, and neural networks went quiet. Between the 70s and 90s, most researchers gave up on neural network. The field splintered. Some chased symbolic AI, systems that relied on logic and rules. Others worked on expert systems, hand-coded knowledge from human specialists, and yet there were a few who never gave up. People like Jeffrey Hinton believed the problem wasn't the perceptron itself. It was that we were thinking too shallowly. The brain doesn't work with single output neurons. It works in layers. But stacking layers of perceptrons made the training impossibly slow. As signals got lost, neurons fired blindly, and outputs made no sense. Until one idea changed everything. In the 80s, researchers rediscovered something powerful: backpropagation, a way to train multilayer perceptrons efficiently. It's just a clever way of figuring out which neuron contributed to the final error and how to send that error backward, layer by layer, using gradient. Gradient is just a way of saying if you change the weight a little, here is how much the error will change the actual existing. That's done by something called gradient descent. So after backpropagation, instead of just drawing one line, now networks of neurons could bend space. It could curve complex twisted boundaries through data. Suddenly, XOR wasn't a wall anymore. It was a bump in the road. This was the rebirth of deep learning. And 30 years after its death, neural networks came back, stronger than ever. Today, they're behind facial recognition, speech models, self-driving cars, and yes, AI like the one you are using right now. The lesson here is deeper than just math. The XOR problem wasn't unsolvable. We just didn't look deep enough. The real tragedy, how many breakthroughs have we missed? Because the first version failed. How many ideas were abandoned because of one missing insight? In science, sometimes the smallest technical bug becomes a 30-year detour, and all it took was a line that couldn't bend. So, next time you hear about a failed idea, ask, did it really fail? Or did we just stop too early? Because history shows sometimes genius isn't about new ideas, it's about not giving up on old ones.